So how do we actually set up a confidence interval? You could see these intervals have a lower value and an upper value. So what did we actually do here? We actually started off with the mean. We took the means and then we added the margin of error and we subtracted the margin of error. We did that in each case. We had the mean and we added the margin of error and we subtracted the margin of error. We also did it here. It was the mean from the sample, add the margin of error and subtract the margin of error. So a generic form for the lower limit and the upper limit. Let's do the lower limit first. So the lower limit here is going to have this form. It's going to be in X bar, but more generically, it's going to be the point estimate. The point estimate in this case was just X bar. And to get the lower limit, we must subtract the margin of error. So we're going to subtract the margin of error. And to get the upper limit, so for the upper limit, we're going to have the point estimate, which in this case was the mean. Yeah. So to get these upper limits, we took the point estimate and we added the margin of error. So this is the most generic form of confidence intervals you have. You can have this as a starting point for any confidence interval you're going to calculate. Now, in our particular case, if we assume that we have we're looking at means, we're looking at the average height, your point estimate will be X bar. And if we assume we have a normal distribution, the number of standard deviations you must add in. Okay, well, let's do this first. It's going to be your critical value times your standard error. This is the number of standard deviations. This is the number of standard deviations. But when we're dealing with the X bar distribution, remember that we call the standard deviation the standard error. So it's the number of standard errors you must add in to generate a particular confidence interval. And likewise over here, the upper limit is going to be X bar. This guy is going to become X bar plus, and the margin of error is going to become the critical value times the standard error. Now, let me take a specific case. Specifically, if we're dealing with a normal distribution, the critical value will actually be z of alpha over 2. And the standard error may be sigma over the square root of n. That's the standard deviation for the X bar distribution. And this is how we're going to calculate. Likewise, on this side, this is going to be X bar plus z of alpha over 2, the critical value, times the standard error, which is sigma over the square root of n. So this is a particular case. This is the particular case where we have a normal distribution. There are other cases which we'll mention in a moment. But before we get to that, what is this z of alpha over 2? Well, let's do a little bit of housekeeping from up here. Let me redraw this a little bit further down to here. Just going to draw the same thing. So we're trying to generate a 95% confidence interval, as we did above. This area in here is going to be 95%. And the area on the side bits, or the tail bits, the side bits are the tail bits, this area in here is going to be 2.5%. And the area over here is also going to be 2.5%, giving you a total of 100%. Now, this is a specific case of a confidence interval, a 95% confidence interval. We didn't have to have a 95% confidence interval, so let me put a more generic form. The confidence a 95% confidence interval is made up of a 95% confidence level. And more generically, this confidence level I write as 1 minus alpha. So alpha in this case has to be 5%. So 1 minus 5%, 100% minus 5% is 95%. Alpha is in fact called the significance level. So significance level. It's called, so there you go, alpha is the significance level. So for this particular case, if we have 95% corresponding to 1 minus alpha, which we've established is 2.5% on each side, then in terms of alpha, what is the 2.5%? Well, here, alpha is 5%. So 5% divided by 2 is what this is, and this is 5% divided by 2 as well. So doesn't that mean that in terms of alphas, this area over here is alpha over 2. So if alpha is 5% here, and then this is 2.5%, which is half alpha, so that's alpha over 2, and that is alpha over 2 there as well. So that's just a bit of a definition. How are we actually going to work out that critical value though? The critical value is going to be the amount of standard deviations we must add to generate a particular confidence interval. Well, let's assume that we have a normal distribution, and we'll look at another scenarios a little bit later. If I want this area in here to be 95%, then this will be the critical value. And the critical value in this case is going to be called Z of 2.5%. So it's basically the area in here. Z of 2.5% means that the area in the tail, in the end bit, this we call the tail bit, is going to be 2.5%. And so to calculate the critical value, to give you a 95% confidence interval, this is telling you how many standard deviations you must add to the mean to get a 95% interval estimate. We can just calculate that in Excel as norm.s.inverse, so norm.s.inverse of the area to the left of this point. If the area to the right is 2.5%, then the area to the left is 2.5 to the left, 97.5 to the right, or 0.975 to the right. And we can just pop over to Excel and do that. Let's do that in Excel. So that's going to be equals norm.s.inverse, and it's going to be 0.975. That gives us 1.95, 1.96. Let's go with 1.96. So this equals 1.96, which is interesting because for the empirical rule, it says to generate a 95% interval, or to grab 95% of the observations, you must add approximately 2 standard deviations. And that was an approximation. The actual figure you must add is 1.96 standard deviations.